First off, welcome to BYU. We call it the University of Hard Knocks. Our motto here is the impossible takes the day longer. The video you are about to see is of a new revolutionary internal combustion engine. First invented by a man by the name of Nicholas Otto, a German who was granted a patent on August 14th, 1877. And the old adage is, if it ain't broke, don't fix it. We just make it better. I'm Len Waller, co-inventor of this new internal combustion engine. Before I start, I'd like to thank a couple of people. First off, my wife, Margaret Starr Peggy Waller. I'd like to thank her for putting up with me for the past 56 years doing all kinds of crazy inventions. I'd also like to thank an old friend, Mr. Douglas Roach, for believing in us when no one else did. Thanks, Doug, for your business expertise, and I won't forget you. My sincere thanks go to my co-inventors, my kid brother Donald, my oldest brother Francis, and also to my uncle Bill Godovin. They are all now deceased, but I promised them that I would go ahead and get this invention out to the American public so that they can see that there are things out here that can give you better mileage at a cheaper cost. Also, I'd like to say a word of thanks to my neighbor for giving me some of these models that I've got sitting on the table over here that we will show later on, and the comparison between the Waller engine and the conventional engine of today. A special thanks to my son, Brian, and his nephew, Justin, for making this video. After years of research and design, the first of many patents were issued to the Waller Group on their sinusoidal cam engine. As you view and hear this engine running, remember this engine was handmade by the four of us, and basically in my backyard on antiquated machinery. Also, I'd like to explain something else before I go any further. The BYU is not Brigham Young University. That stands for Backyard University, taught by the moms and pops of this great US of A. Now let me tell you a few things about the advantages of the Waller Sinocam engine. First, we were told what we were doing at the beginning was impossible to do, but we didn't know it, so we did it anyway. First and foremost, this engine, 4 cycles in 1 revolution. With this type of universal cam that we have here, it can be used on various engines, and there's a big difference between our cam and the standard cam, which I'll show to you later on. The conventional engine of today takes 2 revolutions to complete its cycle. The cycle is intake, compression, fire, and exhaust. This engine does it in 1. Plus the fact we can crossfire. So if you have an even number of cylinders, like an 8-cylinder, you can fire 4 cylinders in front and 4 in the rear. And these cylinders we have are parallel to the main shaft. They are not vertical. Being parallel allows for an even, smooth rhythm of the pistons going back and forth. With the 4 cycling of this particular engine, you can fire pistons in the front as well as in the rear. That way there you're getting what they call a crossfire. That will double up again on the power output. We also have in this engine no babbited bearings. Everything is done on roller bearings. Roller bearings, you put that on a flat surface and they will last a lifetime almost. The engine is also designed in 2 identical halves. You make the front half, the back is exactly the same thing. With that feature that you have there, you can take and change this particular engine, which is a 0.9 liter, all out to a 1.6 liter, just by taking the engine, unbolting it in the middle, take the main shaft that you have in there, which is sinusoidal curve, actually the crankshaft to your knowledge. That sinusoidal curve has a 2-inch stroke on it. I want to put it in a bigger truck, so I get a 4-inch stroke. All I do is now take the engine apart, pull that shaft out, put the new 4-inch in it, and put a 2-inch spacer in between it, and I've changed this engine from a 0.9 liter to a 1.6 liter. And that's the only thing you have to do to it. Another advantage, this has a, let me just walk over here to this table. This right here is a standard camshaft that they have in basically all the engines. And each one of the engines, you have to have a different cam. So if you got a 2-cylinder or up to a 20-cylinder, they're all different. This is my camshaft that we have in this engine. That lift on here is identical to what's on this cam over here. It has 2 lobes on it, 1 intake and 1 exhaust. It sits in a recess on the main shaft of the sinusoidal curve on a pin. Therefore, you have no timing gears and no timing chain. You have 1 in the front of the engine and 1 in the back of the engine. By reversing the 2 of these and changing them, now that same engine will run in the opposite direction. When it runs in the opposite direction, you get perfect centerline thrust. And you can put that in an airplane or a boat. You don't have to build special engines. The crankshaft over here, you have to have a different crank for every engine. This is actually our crankshaft right here. It's a sinusoidal curve. You look at it, and it looks all twisted and curved. Right over here. But the unique thing about this is half of the engine. This is intake, compression, fire, and exhaust in 1 revolution. 2 revolutions in the conventional. So therefore, you got 1 on the front here, and you got 1 in the back. So therefore, you have basically 2 engines perfectly tied together. You look at this and you think it's all twisted and curved. This is a perfectly flat bearing. We don't use crown bearings. You put a perfectly flat bearing against this surface over here. And if this is 1 inch, you have 1 inch of line contact. You got 0, 90, 180, 270, back to 360, which is 0. As this rotates around here, you notice this is thick and this is thin. And it's thick over here. What happens over here is you have 1 inch of line contact going on the bearing. When you get to 90, you have 1 inch of line contact, but you come back to 45 degrees, what's happened is now you're getting a spiral effect around the bearing. On one side it's right-hand spiral, on the other side over here it's a left-hand spiral. So what you have is a connecting rod for your pistons with bearings in it to ride on this surface. If this is 1 inch wide, you put 1 inch and 3/1000 clearance between the bearing to allow for oil, and this does not bind. That's why this thing is thinner and then thicker. Plus the fact, like I said before, if you have an even number of cylinders, you can crossfire. So you fire 1 in the front and 1 in the rear. If you have a 2-stroke, what that does on it, if you have an 8-cylinder and 1 revolution around, you get 16 firings in 1 revolution, because it doubles up again on the power output. That basically explains the sinusoidal cam. The conventional engines of today have a piston in them. Piston has 1 on this side here, and it runs vertical. We decided that's an awful waste. Why not put another piston on the other side and run it vertical? So now when this rotates here and this is in the firing position, the piston on the other side is in the exhaust. So you can have any number of cylinders, whether it's 2 or 20 or 30, it doesn't make any difference. It still functions the same direction. This over here is our first little model that we made, and it's kind of difficult to see, but if you look over here you'll see the pistons, and inside here you will see the cam, which is the sinusoidal curve. As that cranks back and forth this way, there's a piston that goes back and forth here with bearings on it, and that forces the piston over here to go back and forth. So when this fires, it pushes on one side of the cam and causes this to rotate. If this was a 6-cylinder, I mean 8-cylinder, you can fire this one and this one at the same time. That's where your crossfire comes in. If it's an 8-cylinder, 2-stroke, I can fire these two and these two, which comes to 2 highs and 2 highs. So I can fire 4 pistons at one time on a 2-stroke engine. That gives you a tremendous amount of power and torque. Also, with a conventional engine, the stroke that you have, like on this crankshaft over here, is very small. If you've got a 1-inch or 2-inch stroke, that's a 1-inch offset on the crank. And by turning that 1 inch from 0 to 180, that gives you your 2 inches. Ours is a little different. You go from the perfect center line of the main shaft, or the connecting rod, to the center line of the main shaft. And on this particular engine here, it's 3 1/4 inches. But you come down this inclined curve, it's 5 1/4 inches. Now you add the two together, that's 8 1/2 inches of leverage to move 2 inches. Now I'll show you a little thing here in the back that's kind of interesting. Walking over here. This engine here has 110 pounds compression on the cylinders. It's a 6-cylinder motor. I could take this 9-inch balance wheel here and I can turn this engine over by hand. I defy you to take a conventional engine and try to turn it over by hand. That is the leverage factor that you get out of this. So this leverage on here is 8 1/2 times the leverage you would get on a conventional engine with a 1-inch stroke. The crankshaft, when it's made, is made so if you drew a line down the center of it, 1/2 is equal to the other half, so therefore it's perfectly balanced. You don't have to balance the crankshaft on this. That's one main advantage that you have with this one over here. Going back to the camshaft being the same lift that it has on a conventional engine, what we do is put a longer dwell on the top of that cam, the circular cam, and purge that engine of all the dead gases that are in it. We are already working on a new design that's already perfected, and we're ready to get the patent set up on it, that eliminates the valves completely. It has no intake or exhaust valves in it. By doing that, you take 700 pieces off of the conventional engine of today. We'll go into more on that later on the next video that we set up. The engine, like I said before, is very lightweight. It weighs about 1/3 less than a conventional engine, no matter what you have, whether you have an 18-wheeler or a little small foreign car. Has very high torque. I've already explained the leverage factor on it and the balancing on it. It has no flywheel because the sinusoidal cam is its own flywheel. All you have to do is put teeth on the outer side of that, and you can put the starter onto that. So you don't need a flywheel. That takes an awful lot of weight, plus the fact of the cost. This engine will idle at 50 RPM. You don't idle it at 800 or 900 like you do in a conventional engine. You're saving gas again at that point. And if you notice over here, I have a jack shaft going back on here. On that jack shaft, you have your starter, your alternator, and all your accessories, your AC pumps, and everything goes on the jack shaft. There's nothing that goes on the engine at all. So therefore, this engine has bolts on here for the motor mount on each side, disconnect the fuel line and the linkage, and I can lift this motor out. Now the total weight of this engine is 98 pounds. That'll fit in a mid-sized car. We ran this on a dynamometer at 1350 RPMs for 65 minutes on a gallon of fuel. I think it will do better than that once it's a little more perfected. This engine will run on diesel, it'll run on kerosene, it'll run on steam, also it'll run on air. It's really being set up now to be running on natural gas because we have over 200 years of natural gas in this country. And that would be the way to go because it's a much cleaner running engine. And if you notice here, this is an experimental carburetor. This is the exhaust here, and this other one over here is the intake, right here. Now what happens over here is the exhaust is coming through the lower half of the intake manifold. With that, you get your atomized fuel that comes from your carburetor, goes into this heat chamber, and it vaporizes. So this engine is running on vapor. This particular engine has well over 780 running hours on it at the present time. They really test these in the automotive industry at about 100 hours. This one here seems to have very good wear because there's no gravity bearings. Everything is on roller bearings. It has only 7 pounds of oil pressure, which is thrown out to the center of the engine. By centrifugal force, it lubricates the backside of the pistons, which you can't do in a conventional automobile. The horsepower is unlimited. You can have 1 horsepower or 3,000, whatever you want. You just name it. Just build a bigger engine. You can put it in a steamship and run it on steam, and that'll power the whole ship. Like I said before, the oil pressure is only 7 pounds of oil pressure because it's thrown out by centrifugal force and lubricates everything. At the present time, we're looking for interested people that might want to go ahead, or heavy investors in companies that might want to go ahead and get involved in our endeavor and make these engines, compressors, or pumps. Speaking of that, I could run this engine on the front half, make a compressor out of the back, all built in the same one. There's been publications in the past on this particular engine in Motor Trend Design, also in the Nike magazine, which is a Japanese top engineering magazine. It's been on Area TV's Channel 13, My Fox Tampa Bay. It's been on Bay News 9. It's been in the St. Petersburg Times. And it's also in Automotive Engineering. And now we're trying to put it on YouTube just to let the people out here know that there is an engine that will accomplish what they need. So for more information, you can contact me at email right over here at cw8385 hotmail.com, or we can also contact Justin over here, and you can get information from him, or he can send it to me and I can get the information back to you. I can't see the light over here. If you want to take and view this particular engine, you can fly in to the Tampa or the St. Petersburg airport and check on your scheduled flights. You could be in the one in the morning and out in the afternoon. We're only about 30 or 40 minutes away north of Clearwater in Palm Harbor, and it doesn't take that long to go ahead and come in and take a look at it and check on it. So thanks for taking the time to view this engine. I hope you've enjoyed it and you had a look at the future of tomorrow. One last thought that I have over here is I have my favorite chair that I sit down in and do a lot of my thinking, and I think I'll go over there and sit right now. But before I do, I gotta get my favorite drink, root beer. This is Uncle Root's drink. That's Uncle Root's beer. Now I gotta sit down over here and do a little more thinking. idle down there when it's still a little bit rough. I got to bounce those carburetors on it.